Question 9. This is looking at solar radiation. State the Stefan-Boltzmann law for a black body. Now, this over here is the Stefan-Boltzmann's law, and it basically is talking about a black body which is a perfect emitter. It means it emits all the energy from that body. And basically what Stefan-Boltzmann said was that the power radiated, this over here, that the power radiated per unit area is proportional to the fourth power of the absolute temperature, or the temperature in Kelvin. So you need to state that in words. So the power radiated per unit area, so it's the power per unit area, so area squared, is proportional to the fourth power of the absolute temperature, or your temperature in Kelvin. Now you can use the formula here, but as long as you explain what each one of these terms means, that would be fine. So it says the following data relates to the Earth and the Sun. So we get the distance from the Earth-Sun distance is 1.5 to 10 to the 11. The radius of the Earth is 6.4 times 10 to the 6. With the radius of the Sun is 7 times 10 to the 8, and the surface temperature of the Sun is 5,800 Kelvin. Now, it says use the data from the table to show that the power radiated by the Sun is about 4 times 10 to the 26 watts. So we're going to use this formula over here. The power is equal to sigma. That is Stefan-Boltzmann's constant. Now you can find that in all your constant values at the front of the data booklet, and it equals to be 5.67 times 10 to the negative 8. And then we need to multiply it by the area. Now the Sun is a sphere, and the surface area of the Sun is 4 pi r squared, or the surface area of a sphere is given by this formula, 4 pi r squared. So it's going to be times 4 pi times the radius of the Sun, which is 7 times 10 to the 8, and we're going to square that, and then we're going to multiply it by this temperature. Now this temperature is always in Kelvin. Now we're given our value in Kelvin, but if we'd been given it in Celsius, we would need to have added 273 to that. So it's times 5,800 to the power of 4. And we put that into our calculators, and we get about 3.95 times 10 to the 26 watt. So that is approximately to be 4 times 10 to the 26. Then it says calculate the solar power incident per unit area at a distance from the Sun equal to the Earth's distance from the Sun. So if we think of it, we have the Sun. Let's draw a little diagram here. Say we have the Sun there, and we have the Earth. We have the Earth over there. There's the Earth over there, and the Earth is over there. This is like a giant football. All the Sun's energy, all that Sun's energy is being radiated in 3 dimensions out. So to find over here, when it says the solar power incident per unit area, we actually have to find this area of this giant sphere, and we need to divide that into the total power radiated to find the total power, the solar power incident per unit area. So basically what we're going to have is that this solar power, let me call this SP, and it's going to be a power per unit area. It's going to be a watt per meter squared. That's going to equal the total, so that's 4 times 10 to the 26, the total power. And I'm going to divide that because, again, this is a giant sphere. We're going to look at the surface area of that sphere. It's going to be 4 pi. But now our R is the distance that the Earth is away from the Sun. So it's 1.5 times 10 to the 11, and we're going to need to square that value. So we're going to do it on our calculators. So we get 4 exponent 26 divided by, I need to put this all in brackets. So I open up my brackets, 4 times pi times 1.5 exponent 11 squared, close brackets, enter, and I get 1414.7 watts per meter squared. So that's what I get. Now, as you can see, I'm all to two significant figures, so I can write that as 1400 watts per meter squared would be my final answer there. It says now that the average power absorbed per unit area at the Earth's surface is 240 watts per meter squared. State 2 reasons why the value calculated in B2 differs from this value. So in looking at this, we have that not all the energy, not all this 1400 actually reaches the Earth. We have a certain amount reflected. So some of the solar energy is reflected, and that's due to our albedo. So there's a total, this would be your total incident power, that would be your 1400, but there's some of it that is being reflected. And then also we have that, you know, when we're looking at this, if I just draw a diagram here, if I've got the solar power, now if the Earth's surface is like this, then we're going to get it spread over per meter. But what happens when you have over here where it curves around and you have it coming in like that? Now, because of this, you're actually having it spread over a larger area. So when this is not at 90 degrees, when it's at 90 degrees, we have it per meter. But over here, this is not 90 degrees. This is an angle that's smaller than 90 degrees. So we can say that the surface of the Earth's surface, I call it the ES, is not always at 90 degrees to the radiation, the solar radiation. And we also obviously have some energy is lost in its transit from the Earth from the Sun to the Earth. Now, show that for the value for power absorbed per unit area of 240 watts per meter squared is consistent with an average equilibrium temperature for the Earth of about 255 Kelvin. So, if I have 250 Kelvin, we've got, it talks about here consistent with an average equilibrium temperature. So that means in an equilibrium temperature, it means that your energy coming in basically equals your energy going out. You're in, so that's your in-out, you're in equilibrium. So at what it's saying, at 255 degrees, you would be having, 250 Kelvin, you would be having an equal energy out. And that would be given by our formula again, our Stefan-Boltzmann, which looks at power radiated. So if I put it into that formula, my power is equal to sigma A T to the 4. But now I'm going to be using 255. Notice that we've got 240 watts per meter squared. So when doing this, when looking at this, I've got a power per meter squared. So I'm just going to power per area, like that would be a power per meter squared. So that's sigma t to the 4. Now we know that the sigma is 5.67 times 10 to the negative 8, and I'm going to multiply that by 255 to the power 4, and let's just do that on our calculators. When we do that, we get about 239.7 watts per meter squared, and that is approximately 240 watts per meter squared. And then it says, explain by reference to the greenhouse effect why the average temperature of the surface of the earth is greater than 255 Kelvin. Well, energy radiated, so the energy radiated from the Earth's surface is longer wave. It's in a longer wave. It's in the infrared range of the spectrum, and this is absorbed by greenhouse gases, your CO2 and your NO2 and your water vapor and so forth. And then these greenhouse gases, let me just call them GH, the greenhouse gases, GHG, re-radiate this energy to be reabsorbed by the Earth. So it basically traps the energy. The longer wavelength gets stored. Basically what happens is that when on the Earth's surface, the incoming light is shorter wavelength. It's mainly in the colors. It's a yellow light. It's a shorter wavelength, and it goes out at a longer wavelength. And it's this longer wavelength, this shorter wavelength isn't absorbed by the greenhouse gases. It goes straight through the carbon dioxide and your water vapor. When it comes out, it gets absorbed. And that's the whole idea with the greenhouse effect. That the glass of the greenhouse allows the light to come through, but it doesn't allow the energy to escape. And D suggests why the burning of fossil fuels may lead to an increase in the temperature of the surface of the Earth. Well, whenever you have burning of fossil fuels, you are always producing carbon dioxide. So the burning, this produces CO2 gas, all right, and also some other gases, but mainly CO2 gas, and this goes into the atmosphere. So you have more CO2. Therefore, you have a greater or an enhanced greenhouse effect, GHE, and therefore you're going to get more energy radiated back to the Earth.